Okay, welcome everybody. How are you doing? Good so far? 3:30 afternoon, I never know if that's a good time or a bad time. I think the party is getting pretty close, but anyway. So I've been doing this session years back, many times, based on using the 325 as an example, and then for whatever reason I stopped doing it for the last couple of years, and then this year they asked me to bring it back, so I revamped it. And it's now going to be based on the 655. And that was actually a lot of work to update all the slides, and a lot of things have changed since those days. So I asked for a table. Unfortunately, there was no table, but I put some pieces of the 655 here on the floor. You're free to take a look at it now or later. But we'll go through the guts of that product in my presentation. Also, if you have any questions, any comments, just speak up. Don't have to wait for the end, because I will probably run out of time. So if you wait for the end, then you can't get your question answered. So go ahead and ask if there's anything that you want to know. So the subject of today's anatomy lesson is the AP 655, and I say cutting under the skin of the AP. I have a pretty terrible sense of humor. I try to be funny sometimes, and so I put links with a real anatomy session, and I compare it with guts and hearts and brains and stuff. Just bear with me. I hope it's still going to be interesting. So this is what's under the skin. So I show you some more later, but we have some pretty awesome customers. I send an email to some of our customers that take our APs and put them in X-ray machines and said, hey, can you take one of our APs and send me some X-ray pictures of the AP? And they actually did it. So thanks to customers like GE Healthcare, Siemens Healthineers, and some other, we have quite a few customers in that area, and they're super supportive. So I'll start with some introduction on the AP65. Just give you some basics. What is it? Some vital stats of it. Some things about aging and life expectancy of the platform. Again, trying to put some links with a living being. So the name here, AP655. It's a member of the 650 series. We'll soon be adding a sibling to that family, the 654. Primary job description of an AP is pretty simple. It's just the interface between the wired and the wireless world, and it just shifts back and forth. That's really all an AP does. It has a bunch of secondary jobs. It's an IoT hub. It does self-locating. It provides reference beacons for locationing applications. It is an RF and security sensor, et cetera, et cetera. The basic qualifications of a 655, it's a tri-radio AP, 4x4 Wi-Fi. One of the main guys who designed the product is right here, so if I say anything wrong, he'll correct me. It has two 5-gig Ethernet ports, and it has lots of additional skills. A couple of differentiators of the platform. It's really our highest Wi-Fi performance AP. I think you will find that it's the highest Wi-Fi performance AP in the market. It uses the latest 6E technology. There's really no compromise on the RF side. We're doing some exciting stuff in filtering. It does, of course, 4x4 MIMO. It has some serious immunity to interference, either self-interference or interference from signals outside, through some patented filtering solutions that, again, this guy, I'm going to keep on pointing you out, Farhan. Has lots of memory, lots of horsepower, so we have lots of future plans where we can expand and build other things on top of it. It's a very flexible and resilient and highly available AP, secure, location aware, and then I mentioned IoT already. The age of my subjects, it's about 14 months old. The AP65 was born in February of 2022. Typical AP, I don't know if you know, but a typical AP, when we design these APs, they have a target life expectancy of about 10 years. We expect them to be in the field selling actively for about 5 years, and then we continue to support them for a minimum of another 5 years. Typically, actually, it's going to be 7, 8, sometimes even more than that. So an AP spends quite some time in the field. The AP655 is a very specialized high-end AP, so there's not a huge amount, but 80,000 of it in the field in those 14 months only is quite respectable. But it's joining, as you heard yesterday, there's 27.6 or so, or 26.7, I forgot, million APs in the field, so it's joining that. So here's some basic stats again. Let me grab my pointer. It's a big AP. A lot of people have seen it in the innovation zone. 260 by 260, or over 10 inches by 10 inches, 4 pounds. It's this big guy here. This is his family member, so it's really the biggest and baddest AP in its family. Okay, so I have another trivia question for you. Some people have already asked and have given that answer. Farhan obviously knows. How many components do you think there are? Total components, little resistors, pieces of metal, everything. How many components are there in an AP, this particular AP? Does anybody want to guess? 1,024. That's a nice power of 2 number. Actually, not that far off, but it's still too low. 2048. Ah, okay. Close, 2,800. So I've been doing hardware for a long time, doing product management of these products. I'm always blown away by how much stuff we built into these APs. And that's really a key takeaway that I want you to go back with. These things are not just simple radios. There's a lot of stuff that goes into this. Also a lot of stuff that can fail, right? The more you put in there, the more risk of failure. And given that, the reliability of these products are actually quite impressive. Okay, so temperature range, it thrives in 0 to 50 Celsius. 122 Fahrenheit for the Americans here. There's quite a few, I believe. And that is typical for an enterprise AP. But keep in mind, that's just the ambient temperature, right? As you probably know, if you deploy our APs or any AP, the actual touch temperature of an AP can get quite high. It is critical that we don't exceed 158 Fahrenheit because that's a safety limit for metal pieces that are user accessible. If you touch a surface, a metal surface that is 158 Fahrenheit hot, it's hot. You won't burn yourself because it's safe, but it's shockingly warm. So the AP does get quite warm. And internally, some of the components that operate, power amplifiers, they can operate at crazy high temperatures. So that's why I'm always kind of laughing when people say we want to build a temperature sensor in the AP to measure the ambient temperature. Because inside of this little box, it's hot. It's very hot. So that's a problem. Yeah, so it has a processor that runs at 2.2 gigahertz. It's running a quad-core CPU. That means 2.2, what is that, billion beats per second. And I looked this up. This is 700 quadrillion beats, heartbeats, over the life of the product if you have it for 10 years. So that's pretty impressive as well, I think. A little bit then about reliability and the susceptibility of the product of basically getting sick, of getting problems. You may not know, but any electronic device, be it your cell phone, be it the smallest little electronic device, or these APs, they are subject to failure. Over time, they will fail. The thing is, how long does it take? And is it an acceptable failure rate for us to still give lifetime warranty on the product, right? Because we would not do that if every product would come back with failures in the first year. So there are some measurements, some statistics or some stats for that are important. So a typical product first, initially when it's young, when it goes through its early days, it has, I think they call it, infant mortality. So in the early days, you see high failure rate. Then it settles on more or less a static or a constant statistical failure rate over the life of the product. And then when it is like 10, 15, 20 years old, it increases again, and then the thing is just dead. This is the main period that you will be using the product, and the failure rate in that period is critical, and that's expressed in what's called MTBF, mean time between failure, and there are targets for that. We use at least 500,000 hours or 57 years. So the time between a failure on a single product, the target that we set for that is at least 57 years. You say, well, okay, so I will only see one failure every 57 years. That's not true. It's a statistical parameter. So if you have 57 APs, you will see one failure every year. If you have 57,000 APs, you'll see 1,000 failures every year, right? So that's how that works. That is a statistical parameter that you can calculate on an electronic device. In reality, we see that our failure rate for the products that we build is actually much better than that calculated number. Typical failure rate for our APs, basically how many failures do we get, how many returns do we see every year? It's about 0.2%. Anything below that is great. Anything above that, some people are starting to get nervous. And then I call Farhan. Okay. So the first thing we do to avoid this period, we do burn-in in the factory. We leave these devices at a higher temperature to weed out those early failures. And then when we ship them, they should be in this constant failure rate mode. Once they're old, and typically that should be at least 10 years, but it could be many, many more years. I know there's still some AP65 out in the field, and those might have been there for 20 years, and they're still okay. But once, at some point in the future, we reach this point where failure rate's going to go up quite dramatically. That's why the word limited is in our lifetime warranty. You should never give unlimited warranty on an electronic product because they will eventually fail. Any questions or comments so far? Yeah. Yeah, so all of the Aruba APs, there might be one or two exceptions, but pretty much all the Aruba APs have a thermal shutdown function. So if for whatever reason, because we have customers that deploy them and then they put stuff on top of them, or dorm rooms are a good example. APs on the wall and then there's blankets and pillows and stuff on top of them. There's no airflow, the AP gets too hot and it will automatically shut down after some time. And then when you remove that stuff and it cools down, it will come back. If you don't do that, they can seriously get damaged. I have some nice pictures of APs where the plastics start deforming. They can get very hot if you don't take care of that. Any other questions so far? By the way, since I haven't done this presentation for a long time and I completely revamped it, I have no idea how long this is going to go. So as I said, I might run out of time, but maybe I'm going to be done in 5 minutes, but probably not. Okay, so here again, so just taking a first look inside, I just wanted to share this. You can't really see much detail, although you see the mount bracket here. This was just by shoving a complete AP into an X-ray machine. And again, this was courtesy of GE Healthcare. I'll go more into the details of what really into this. It's really a sandwich of multiple layers, and they're shown there, but I'll show you what's really inside there. So front cover, simple, right? And I'll talk a bit more detail about what is important. Even though it just looks like a simple piece of plastic, there's a lot that goes into that as well. If you take the front cover away, the first thing that you see is this. It's the antenna plate. There's a whole bunch of antennas. I will quiz you in a minute to ask you which antenna is which. So we're going to find out if you have any idea. Farhan cannot talk. If you take that plate that carries all the antennas and some other stuff, you take that away, this is what you'll see next. That is the main circuit board. The AP655, as most of our APs now, just use one big electronic circuit board. We don't have separate radio cards. When I did the 325 one, we had 2 separate cards on there. Everything is integrated and combined on a single board like this that has all the electrical connections. Now when you take that away, you look at the back, the rear cover, which is aluminum, die-cast aluminum. That's what makes the AP heavy. That's the 4 pounds. But this is a critical part, and again, I'll talk more detail about why this is an important piece of the AP as well. Turn it around, this is what you see, back of the AP. That's the mount bracket, those are the interfaces, da-da-da. Take that out, you see the other side of the printed circuit board with all those components. These are called shielding cans, or the covers of the shielding cans. If you pop those off, which I've done on this sample here, you'll see there's actually a lot of stuff underneath of those cans. And the reason we have those cans is to avoid interference between different parts of the board, and again, also interference that coming in or goes out to the outside world. Then if you take that away, you look at the back side of that antenna plate, and you can see here there's little cables that connect the antennas that are on the other side, remember, of that plate, that connect them to the circuitry. Then if you take that away, you look at the back of the front cover. So it's pretty simple, actually, right? And the whole thing is put together with just 4 screws. That plate is screwed onto the metal back with additional screws, but the front cover is just held in place with those 4 screws. And if you want to take that off, that's why you need those Torx screwdrivers. You need a little bit specialized screwdrivers for that. Comments, questions? No? Very clear? All right. So then if you look at that board again, if you take all those shielding covers off, then you're looking at the actual components that are inside of the AP. And again, I'll go over the details. There's CPU, there's Ethernet components, there's radios, a lot of radios, PoE circuitry, etc. in there. Oh, yep. Switches? There are no switches except for a little press button here that is the reset button of the AP. Other than that, Farhan, correct me, no switches, I believe. There's really nothing to switch, right? You don't have access to this anyway. There are some There's some circuitry here that's only used in manufacturing when we do tests and stuff like that, but yeah, there's no switches. No. Okay, go back then. So skin and bones. It's the housing, the enclosure, and the mounting. So a little bit more detail. So we have this metallic foil logo that is molded into the front of our AP. We like to make it nice and shiny. It's kind of our calling card, I guess. This might change to this logo soon. But we're going to stick with the same look. And on the back, as I said, there's just 4 mounting posts, and these things are what they call LED light pipes. So they basically guide the light from little LEDs, so light-emitting diodes, little diodes that generate light on the board to the front of the AP. So this is the same as here, right? They give you the indicators. And then if you look at the back, it's the back brace. It's not the actual mount. As you know, you need to order a separate mount. This one interfaces with whatever mount we have. We have a little Kensington lock here. I'll talk about the electrical interfaces more. And that's the other side of that piece of aluminum. I used to have a nice video that shows how this piece is made in the factory. And it's actually quite impressive because it's liquid aluminum that's being pushed into a machine, and it's got a huge amount of force, and it just stamps out this big piece of aluminum with a massive amount of force, and it's hot. It's pretty cool. But I don't have the video anymore for some reason, so you're going to have to believe me on that. So, yeah, as I said, the enclosure itself just consists of 2 parts. It's really a plastic front cover and a die-cast aluminum rear cover. All the parts are really contained in that metal piece. It's like a holder for all of the circuitry. And then we have those secure screws. But keep in mind, it's not just a box. It's not just something to make the AP look aesthetic. It's an integral part of the overall AP design. It protects the internal components. It, of course, defines the look and feel of the product. It gives strength and also supports mounting, of course, the AP. It also serves as a heat sink. We talked about touch temperature already. The back of the AP is a massive heat sink. And it also provides additional RF shielding for the components on the board. Yeah, as I said, integral part. We have some customers that take our products, and I mentioned, actually, I don't think GE Healthcare does that. They just take the AP. But you have other customers that want to build the APs into a system that goes in airplanes, for example, or medical equipment, or military vehicles. Believe it or not, there's Aruba gear that goes into Apache helicopters, in tanks. It goes in all kinds of things. But the first thing they do, they take all the circuitry out of the AP, and they build it into a different system. And that's a whole system design in itself. Again, you cannot just take the AP board out of the box and then just assume it will work. It's a complete system that affects the overall performance. So front cover then. It's not just a pretty face for the AP. It provides strength and durability. That's important for the plastic material that we use. These APs, as I said, they can be out there for 10 years. We want them to continue to look good. Don't turn yellow. I have some pictures, believe me or not. It provides the color and finish of the product, and that's important when people, some people want to paint the AP. Anybody here ever paint APs because there's aesthetic reason? So I have a question. Did you paint the actual AP, or did you buy a cover and paint that one? All right, good. Yeah, you avoided warranty that way, right? You know that, no? We're not very strict on that. I don't think we've ever denied a warranty claim. We've had indoor APs that came back that had water in them. Clearly not the type of indoor use case, and we still send a replacement. But strictly speaking, when you paint it, you would void a warranty. It's important, of course, that this front cover is transparent to RF energy. The antennas are sitting right behind it. So actually, this foil here, it's interesting that may affect your antenna patterns, because it could be, it's no longer, I believe, but it could be metal. Now it's a plastic that looks like metal, but it affects the RF performance of the AP. Flammability is important. We want to make sure that if you deploy this in a building, in case there's a fire, there's no hazardous, toxic smoke and things like that. And of course, it's important to not use any banned substances, and try and use as much as possible either recycled or recyclable materials. Most of our products are built using new materials, but they're all fully recyclable. So we're exploring the use of recycled materials, but that is it's difficult to maintain, the aesthetic standards and stuff like that. So, but it's something that's becoming more and more of an issue, of course. Anybody know what a platinum rating is? Familiar with that? Yeah, so I mentioned before, in case there's a fire, there's pretty strict rules if you deploy an AP above the ceiling, or God forbid in the wall, or anywhere in those areas, you need the AP to be plenum rated. So in case that there's a fire, again, that it doesn't generate any toxic gases or hazardous smoke or anything like that. The plastic materials that we use are pretty critical for that. A long time ago, we used plenum rated plastics, and those plastics had some drawbacks. They would, over time, look like that, or worse. I've seen them worse than that. This is actually a picture that was taken not that long ago. That AP has been out there for a while, but UV light on those older plastic had some massive impact. We've since learned our lesson. Newer materials that we use, they do not discolor. They just still discolor a little bit. If you look at an AP over 10 years or so, it will change a bit, but nowhere near as much as this. But that's another thing that goes into picking the right materials. So yeah, since the key thing is what happens when the AP is burned, these are the kind of tests that are being done. We literally put the AP in an oven. This is an older image again, but same idea. Put them in an oven, burn them, very controlled, and then we analyze what comes out, what the gases are and what they look like, and when we pass, we get a certificate, it's all good, and if not, we have to do our homework. After the test, that's how the AP looks. I thought that was pretty nice. So that is a 655 out of the test report for this particular test. This one I thought was pretty nice. That's an older AP, but I just thought that picture was pretty amazing. Extra crispy, maybe? I don't know how you want to call that, but it's, I thought that was pretty impressive. So the rear cover then provides structural integrity to the AP, gives it strength, does the RF shielding, and also is a heat sink. I mentioned that already. Touch temperature, we talked about that already. There are very strict limits on how warm metal, plastic, all kind of material can get if a user can touch it. If it goes over that 70 degrees, then we have to put stickers on there and warnings and all that kind of stuff, and we literally thought about doing that, but it's better to just avoid it and don't have those risks. Let me see how we're on time. Are we good? And then a little bit more about thermal testing. Hardware team, Farhan's team, or the guys in Farhan's organization, they spend quite a bit of time making sure that each and every component that is on that board, when the AP is under max load conditions, those components are all operating at the temperature that they're specified at. And that temperature can be different for any component. A power amplifier has a very different temperature range than the CPU or a memory component. So we put thermocouples on all of those components, and we operate the AP in worst case conditions, and then we see what happens. And then you get a graph, something like this. And this is done in a thermal chamber. I believe this is the temperature of the actual chamber, so the ambient temperature, which goes up to 50, which is the maximum temperature that we specify for an AP. And then we measure all those components, how hot they get. And then we compare that against the specs for those components, and we say, okay, well, if we have no problems, then we have no problems. So some components, I don't know which one this is. I think this is actually the rear cover. Heats up to 60 degrees Celsius. Others go over 100, and hopefully everything was fine and no problem. Interesting thing to note here, it does take 2 hours or so for this thing to reach steady state. You can't just turn on the AP and everything will just be worst case. It takes quite a bit of time for that thing to warm up. So in real life, it would take like 2 hours of worst case conditions for all the components to be at their absolute worst operating condition. So pretty rare for that to happen, but we still tested it away, of course. Mount support, mount always a hot item or a subject I get lots of questions about. But obviously, all of our APs now, they ship at this little bracket on the back or brace, and that interfaces with whatever mount you want, whether you want to attach it to a rail or to the wall or whatnot. We have lots of mount kits. And oh yeah, I have a sample of that. We're finally launching a universal kit. So there will be one mount kit that you can use for everything. So if you want to take a look, I have one in the Innovation Zone that's coming out in the May timeframe, so pretty soon, by popular demand. Sure. No, it's not replacing it, because a universal mount is great, but it's more complicated, it has more parts, it's more expensive, and you might end up throwing a piece. So if you want to be efficient and sustainable, you might want to think about it and say, hey, maybe I buy this dedicated mount that is much more optimized. But if you really don't want to think where and how you're going to mount your AP, you just buy, for every AP you buy, you just buy a universal mount kit and be done with it. Yeah, some customers have no clue. That's a general, true statement. Sorry, no offense. But it is true. Earthquake testing, that's an interesting one as well. So we make sure that the AP can be deployed anywhere. We do altitude testing, we do temperature testing. An interesting testing we also do, we do simulated earthquake testing. So we have a whole document with all kind of environmental test specs, and earthquake testing is one of them. And you would think, okay, that's pretty simple, but you gotta keep in mind that when the AP is mounted to a rail as part of a suspended ceiling, it has a mount bracket, it has that back brace, and then it has an AP that could be up to 4 pounds. That whole combination needs to be properly tested. And then we need to also make sure that after 10 years in the field, it's still safe and it doesn't fall down if there's an earthquake. Again, I have an older video, but I do want to show it. It's pretty cool demonstration of what happens when you do these earthquake tests, and maybe one of you can tell me which AP that is. But that's literally what happens. No, it's not a 105. It's a 135, right? And so in the past, I used to get questions, hey, those plastic brackets, they're really not secure enough. And then I'm showing them this video. We've done a lot of testing. Those brackets were fine. That was not the reason we went to metal brackets. It's basically to stop people from asking us, are those brackets a problem? Because we got that question a lot. Since the 500 AP, we have, actually, yeah, the 500 was the first one we have these metal brackets. Before that, they all have this. We're bringing it back on the 503, actually. So, because it is also cheaper, and the 503 is, the intention is to be low cost. So these brackets, we're actually reusing those. But yeah, it's just an example of the kind of testing we're doing. Yeah, and that's a 135. Yeah. Okay. Yeah, of course, protection from the elements, not to be confused with the element. Of course, for enterprise products, the requirements are a lot more strict or more aggressive than for a typical consumer product. We test up to 50 Celsius, we do earthquake tests, we do a lot of other testing. But the next step up from an enterprise-grade indoor AP would be our hardened or industrial AP. We have some 518s, 318s, and products like that. Those have increased operating temperature range. We do more shock and vibration tests. We do protection against dust and water penetration. Not full outdoor, but still those are resistant. They can handle dust, they can handle dirt. They cannot handle rain. And then, oh, wrong clicker. And then, yeah, outdoor products will take it to the next level. Was anybody there at Atmosphere when we did this? We had we had an AP sit in a fish tank for the whole event. I'm not going to say what happened to the fish. We bought another one. Had nothing to do with the AP, I promise. So the outdoor products will take it to the next level. They're fully rated, fully waterproof. They can go in a fish tank, but they can also be deployed in the rain, anywhere. And our APs, we're pretty proud of those. They're quite hardened. You can deploy them anywhere. There's no heaters. They will start up in any temperature as well. And then, of course, we do additional testing for specialized environments, medical environments, clean room deployments, or transportation is a good one, on trains, on buses. It all depends on what AP model you have. That doesn't apply to every AP, of course. And then the other one here that Jared is not here, but that's his favorite, the hazardous locations, where we want to make sure that an AP does not start. Some people call it explosion-proof. The AP is not explosion-proof. The thing of this this type of testing is to make sure that an AP doesn't cause an explosion. So if you're in an environment where there's flammable gases, explosive materials, whatever it is, the AP can be deployed there. So we have some special models where we go through those tests. Questions, comments, Jim? Yeah, good point. So for these hazardous locations, there's actually a lot of requirements. There's things like impact tests that are done so that the AP doesn't break in case it gets hit by something, which I don't know why that's part of it, but that's part of it. The other thing is indeed, any interface need to be secured, and there are very strict requirements. For example, all the Ethernet ports, they need to be attached to conduit. You cannot just put a cable and go with it. So we need to have an interface that supports conduit. Temperature rating of your enclosure is critical. Antenna interfaces are another area. The type of antennas you can use, there's lots of things. And we go like half the way. We don't go all the way, right? There's different classes of hazardous locations. We take it one step in there, which addresses the majority of refineries, mines, and stuff like that we can deploy, but you can go beyond that. And that's where we have partners like Analink, Extronics, and others that actually take the AP and put it into, I don't know if you've ever seen those enclosures. They look like a safe. I mean, it's crazy how much security is around that AP. Costs is pretty expensive as well, of course, but yeah, we just go one level up. Oh yeah, I wanted to show this video. So some of the tests that we do to make sure that the APs are what they call IP rated. IP rating addresses both dust and water. The first digit is dust, the second digit is water. Our APs are IP6, the outdoor APs are IP66 and 67. That means that they have to handle stuff like this, where somebody literally has the AP rotate and has a jet with a well-defined nozzle and pressure and just subjects the AP to that kind of behavior. And then we open up the AP to make sure that there's actually no water inside of the access point. Okay, basic building blocks. So again, I'll do some analogy with human, parts of the human body, I guess. First part, brain, CPU, memory, TPM. I'll go into that a little bit more. Sensors are the antennas and the physical interfaces of the AP. Guts, radios. We obviously have 3 radios, 3 Wi-Fi radios. We have a BLE Zigbee radio. We have another radio, but I have it classified a little differently. And then lots of filtering. Talked about that already. Power distribution for the digestion, for the distribute energy throughout the AP, which is actually not as simple as it seems. It's not just PoE or DC power in, and then the AP will have power. Bringing the appropriate amount of power and the right voltages to every individual component is a whole job in itself. I call it 6 cents. So we have a GPS receiver on board of the 655, and there's some more stuff that goes into that, so whatever. And then again, I didn't know how to classify this, but there's lots of shields and other pieces that go into the design that cover up parts of the circuitry, etc. You know what this is, right? You're familiar with this one. I probably took it from you. So this is the overall block diagram of the AP. I'll go through some of the parts individually. So this is the, which I would call the brain. It's the actual CPU, or it's actually an SoC, so it's a combination of CPU and some other components. Again, I'll get into that. Memory, TPM is here, I believe, and some other parts that are part of that. This is what I call the sensors, the antennas, lots of interfaces around the AP as well. These are the guts, radios, and then how all those interfaces get connected to the rest of the product. This is all the power distribution, and it looks way simpler here than it is in reality. I don't know how many of those 2,800 components are involved in this part of the block diagram, but it's quite a bit. And then the GPS receiver sits there as the 6th sense of the AP. All right, diving into the CPU. It's not easy to pick the right CPU or processor for an AP, although sometimes we just work with our partners, Qualcomm, Broadcom, and they have something canned, and we can just go with that. But they have lots of choices, lots of options. Picking the right one is critical. Of course, cost goes into that. Power consumption is critical. Performance, always very important. And certainly on a 655, where we don't really take any compromises, make any compromises on performance. That's a critical one. And then what kind of interfaces does it support? We want to have USB, we want to have 2 Ethernet ports, etc. And sometimes, as part of that CPU is not there. So yeah, if you care, we use what they internally call the Hawkeye system on a chip. So a system on a chip combines CPUs. There's actually radios as part of that same component integrated and a bunch of other stuff. There's 4 cores. It also has 4x4 radios on both 5 gig and 2.4 gig. This SoC does not have the 6 gig radio integrated in it. That's a separate circuit on the board. Has a bunch of Ethernet MACs. It can go all the way up to 10 gig, but we only use 5 gig. There's no need for 10 gig. Has a bunch of USB interfaces, serial interfaces, etc. And on the board, oh, I was going to go to the flash first. We have, okay, this is one conclusion of this. We have lots of flash memory. We have lots of SDRAM memory. There is, as I said, 4 gig of flash. There's 2 gig of SDRAM. I'm not quite sure how much of that we use today, but I'm pretty sure it's just a fraction. We have lots of plans moving into the future where my software colleagues keep on saying we need more memory to allow us to do all those fancy plans that you have and containerization and whatnot. So we're building this product to last for the future to open out those capabilities. So there's plenty of space available. The TPM, you guys familiar with what TPM does? It's basically just a module on the board. It's actually just a tiny little component on the board. I had a hard time finding it, but it contains certificates and it can do store secure credentials for the AP, and it helps us in many ways. We can secure the connection between an AP and a controller or the AP and central. We can store certificates in there that also help us to avoid counterfeiting of the product. People cannot run our code on a product that doesn't have the TPM, or they cannot run other people's code on our parts. So there's lots of things where TPM helps. So these are what those components are. So on the board, this is that SoC, that Hawkeye SoC that has the CPU and lots of other components. SDRAM, 2 components here. The TPM part, I finally found it. Please don't tell me, Farhan, that it's the wrong location, okay? Flash is here, and then NAND flash here, NOR flash here. So we have 2 pieces of flash. One is a little bit more, I would say, robust, but it's more expensive. We do the basic AP boot comes out of that, and then the huge piece of flash is a little bit more error-prone, I would say, so there needs to be some error correction happening there. That's where we store the basic images. But we boot out of NOR flash, and then we run the code that comes out of the NAND flash. Any questions? I'm getting extremely thirsty. I'm the only one talking, so yeah, there you go. Okay, external interfaces. So first, of course, yeah, got 2 Ethernet interfaces. An Ethernet interface, as you know, they're for data and power, PoE power. We have 2 wired internet network interfaces. Both are RJ45 plugs. They are fully interchangeable, although I was just talking to somebody who said, failover, there's some restrictions there, so they're not exactly symmetrical. But in theory, they are fully interchangeable. Both go up to 5 gigabits per second. In most of your deployments, you probably won't need that to go all the way up to 5 gig, but you potentially can. You can lag them, or you can do failover between the 2. Yeah, so if you, it is pretty easy on a radio, on an AP like this, in a lab environment, to push so much data through the AP that you can easily exceed 1 gig. However, in most of the real-world deployments, we won't see that happening. So I always ask this question, maybe one of you can help me with this. If there is a customer who has ever seen an AP, any AP, our AP or another AP, that actually in a real world deployment that pushes more than 1 gig of TCP data over the wired ports. I've not seen it yet. Nobody's going for it, huh? Oh, you have? Okay, yeah, I guess if you do a VR dedicated setup, you probably can get that. I would compare that almost to our lab setup. And I've talked to people that sometimes in dedicated areas, you would turn the APs into a mode where you do the widest channels and everything is optimized, or you do a file transfer in those locations, maybe you can get there. But typical use case, it's pretty rare to get to over a gig. But anyway, if you have to, you can. We have a USB 2, it's still USB 2. We will at some point go to USB 3, but right now there's not much need for that. USB 2 port that can supply up to 5 watts to an attached device. You have seen some devices maybe in the innovation zone. We have BLE dongles. We have an LTE dongle that can be inserted. There's a bunch of other devices, and there's more coming. We're working on a sensing radio and some other stuff that we'll offer. But more interestingly, we have a wide ecosystem of partners that do IoT devices that can plug into the USB port. So it's a pretty critical port. In the future, our IPs might have more than one USB port just to support more of those use cases. If you want to do air quality monitoring, weird things like gunshot detection, or if you want to do electronic shelf labels, you can take advantage of that USB port and plug in one of the devices from our partners to do that for you. Console port. Does anybody want to complain about our console port? Oh, yeah, some people, I'm sure. You have a question, or you're also complaining? No, we don't. There's very few exceptions, but the majority of our APs, the indoor APs, we don't provide PoE out. Both of them take PoE in, and they're fully interchangeable. And on the 655, actually, we implement a mechanism where you can combine power from both. Because the 655 is a big AP, it needs a lot of power. And if you have a single AT PoE source, that may not be enough to operate the AP without restrictions. And if you're not ready to change your switches, you can use both ports, and then we can combine power from those two switch ports. But at this point, we don't have PoE out on the APs. The max what? That's also, it's a good question, but it's a difficult one to answer. Well, no, it's easy to answer. I can say 41 watts. So that's what it says in the data sheet. The AP655 draws up to 41 watts, but that is absolute worst case. You know, we're very, I guess we're conservative. We want to make sure that whatever we put in the data sheet is absolute worst case. That depends on environmental temperature, whether you plug something in the USB port, whether both Ethernet ports are used, but mostly how do you configure the radios. If the radios are only transmitting at 21 dBm ERP, you're nowhere near that maximum power consumption. So there's a massive variation between what an AP consumes in idle mode and what it consumes in worst case mode. That could be 2x or more between the two. So that's something to keep in mind, because people often say, well, it can consume 41 watts, so I have to go to a higher order PoE, you have to go to class 6. You might not have to. It really depends on how you deploy the product and what you're doing with it. Yeah, just one comment, by the way, on the console port. So the reason I said, if anybody wants to complain, yeah, I have some if you want. We have a proprietary interface. There's some reasons for that. It has to do with cost, it has to do with complexity, and we kind of standardized on that. If you want to access the console port interface, you need a proprietary adapter cable for Aruba. For the indoor APs, outdoor is a little different. So that's something to keep in mind. It's not a standard USB port. And whenever somebody then complains, I say, I have some of those cables, so I'll give you one. So anyway, and then usually they're okay. Was there another question? Or? Oh, yeah, good point. Yeah. So one thing that we did, because we still have customers who like to go back to the old traditional RS-232, RJ45 console port that many of our competitors still have on their products as well. So we said, well, no, we have a proprietary one, but we did introduce an adapter module that you can plug into this interface, you power it off the USB port, and it brings back that old RJ45, RS-232 interface if you want to use a console adapter or whatever it may be in your setup. It usually only gets deployed in people's labs. It's not common for people to use it in an actual deployment, but it does happen sometimes. Yeah. So we have a solution for that. Pretty much all our indoor APs support DC power, of course. It's 12 volt on this one. And we use a standard adapter that we've been offering for quite a while. And then we have a little button there, a little hole there. That was the button I was showing before. Keep it pressed, the AP resets the factory defaults. If you press it very quickly, many people don't know that. If you just press it, you toggle the LED functionality, so the LED will turn off, or it will go back to its normal mode. So yeah, obviously we have 4 LEDs. We have a couple of different modes. In software, you can put an AP, the LEDs into a blink mode. That helps sometimes to find an AP. Sometimes you have too many APs and on your console, you don't know which AP is which. You put that AP in blink mode and you can see which one it is, little things like that. And you can turn them off, of course. 3-color system status LED, and then 2-color for the radios. Each of the radios, so we have 4 LEDs all in all on this AP. And they are here. This, by the way, was by popular demand. In the previous generation of 5XX APs, they were on the side, and people didn't like that because you can't see them from every direction. There's different classes of thought, schools of thought when it comes to LEDs. Some people want lots of LEDs. They want an LED for every function, so we can easily debug, and we can look, oh, that one's green, so it's all good. Other people just want one LED or no LEDs. They just want a green, red LED. So we kind of compromise. We've gone back and forth. Previous models we had 2, now we have 4, but yeah, that's really up to what everybody prefers. You guys familiar? Did anybody go to the antenna? There was an antenna class already, right? Did you guys cover antennas? No, a little bit. Anybody go to the antenna classes? Okay. So I don't want to talk too much about antennas, but I do want to highlight, people talk about antenna gain, but antennas don't really provide any real gain. It's a passive element, right? It just focuses the energy. It's good to keep that in mind. We say, okay, well, we go from 18 dBm to 24, so the antenna provides the gain, but that's just because it focuses the energy in a particular direction. It is not adding additional energy. And by doing so, you go from what is usually just a sphere, you focus the energy in a certain direction, and you get a pretty complicated pattern. I don't want to talk too much about antennas, but I do want to show this picture here. This is not an antenna of the 655. This is a sector antenna. And you can see that in one direction we focus the energy. It has a high gain there, but that goes at the expense of energy being directed in the direction. Side view looks like this, and 3D it looks as messy as this. This is actually a pretty clean one. Antenna patterns are, in 3D, they look pretty ugly. And it takes a bit of understanding of the whole thing to be able to read those. So here's my next quiz. So these are all the antennas of the AP. Anybody wants to guess which one's which? I thought I had time to take a drink while you were shouting out what it was, but I didn't talk about polarization. That's, by the way, that's another thing. Most APs use either all vertically polarized antennas or they use a mix of vertical and horizontal. And what that means is that you can imagine it that the energy in the air that's coming from an antenna can either be bouncing up and down in a vertical direction or horizontal direction. If an antenna is horizontally polarized, the energy goes this way, and then it propagates. And in theory, if you have a perfectly horizontally polarized signal and you have a perfectly vertically polarized antenna, you will not capture that signal because they're perpendicular. In real world, of course, that doesn't happen, but we use a mix of vertically and horizontally polarized antennas, and that typically gives the best result. Horizontally polarized antennas are more complicated, so I'll give away that all of these structures here, those are all the horizontally polarized antennas. They're little PCBs that are they're a little bit elevated from the metal plate. All the other ones, which are very simple metal structures, those are vertically polarized antennas. Higher frequency means smaller structures, typically. Depends a little bit, but the higher you go in frequency, the smaller the structures become. And we have a total of 10 antennas on the AP655. We have 2 6 gig vertically polarized antennas. Those are the tiny ones over there. We have 2 6 gig horizontally polarized antennas, those. 2 that are dual band, 2.4 and 5 gig. Because remember, we have 3 4x4 radios, so you would expect at least 12 antennas. We only have 10. That's because we combine 2.4 and 5 gig on a single set of antennas. These are the vertical polarized one, and then we have the horizontally polarized, those big black guys there. And then we have 1 antenna for BLE and Zigbee on 2.4 gig, and we have 1 GPS antenna, which is at the lowest frequency that we support at 1.6 gig, and it's also, for that type of antenna for vertically polarized, the biggest structure on there. You guys still awake? Not falling asleep? Good. I have 25 minutes. I think I'm going to make it. Anybody ever look at the antenna patterns in the datasheet for APs? Are you quite familiar how that works? Yeah. So this kind of illustrates, but this shows an interesting point, right? So if you look at the antenna pattern around the AP, so this is looking at the AP from the front or from looking at it up if you want. This blue line is the pattern that's basically in your ceiling. It's the pattern at the level of, it's the true horizontal plane in the plane where the AP is at. The gain there is actually not as high as you would like, well, as you would think it is. The maximum gain for these type of antennas is under an angle. We often describe it as kind of a cone coming out of the AP, and you can see that here as well. The highest gain is not in this vertical direction, is not in your ceiling, but it's actually under a down-tilt angle. So we document both, and that's actually a significant difference in the gain between those two patterns. All that means is that these antennas are really not perfectly optimized for maximum distance in a horizontal direction. If you want to maximize that, you're better off using those dipole antennas, stick antennas, and use external antennas on the AP, because those have a true omnidirectional pattern around them. And if you do deploy those antennas, don't deploy them the way that they've deployed them here, okay? Because you want those donuts to be like that, right? You don't want one to be like this and the other one like that. It's just weird. Are there any here? I don't know, but they're in the other rooms at least. So this is looking at it from looking up to the AP, and this is looking at it from the side. So again, actually right underneath the AP, you typically have a little dip. In some cases, if this is an average pattern, that dip can actually go all the way, and if you're standing right under the AP, I've never been able to experiment with it, but theoretically it's possible you basically get no signal, even though you're right under the AP, because there could be a null sitting here. Okay. Main internal functional blocks. Ethernet is actually pretty straightforward. The first thing that, when you plug in the cable, the first thing that signal sees is basically some magnetics, a transformer. And in our case, those magnetics are actually part of the plug on the board, or the jack there. There's a little metal piece that has not just the connector, but there's also a transformer built into that already. That's called a mag jack, I believe. On the other side of that, we go into we buy our components from Aquantia on this side. In this case, they convert the analog signals from your Ethernet port into a digital signal that then interfaces with the system on a chip component. In between, part of the function of those magnetics is also to take out the PoE voltage from the different signal pairs on your Ethernet interface. So we take that out, and we provide they also provide isolation between this side and this side of your circuit. Those are pretty easily identifiable on the board. Oh, already said that. And then we go back to the rest of the whole Ethernet interface is implemented on the system on a chip. So that sits here. Those are those connectors. On these APs, we have side entry for the Ethernet ports. In the past, we used to go this way. That's another subject for discussion with some people. There's different schools of thoughts on what's the best. Goes in here, the PHY components are here, and then there's lots of other components involved, but eventually it'll go into the system on a chip here. I'm not going to talk too much about this. I think that was covered probably in your presentation quite a bit. But it is important when we talk about RF power from an AP, we typically, in our GUI and CLI, when we talk about RF power, it's always in terms of ERP. And ERP, effective isotropic radiated power, it includes not just the actual physical power that we transmit out of the radio, it also includes what we call MIMO gain. If a radio is 4x4, we have 4 change, we have 4 times the amount of power, so plus 6 dB. And it also includes the antenna gain. And again, antenna gain can be anywhere between, well, it can be anything really, but for a typical AP like this, it's around 3 dB. But keep in mind again that energy, that 3 dB gain, that is in a particular direction, in a 3-dimensional space. So you say, okay, I have an AP that has 3 dBi antenna gain. It must give me a better performance than this other AP that only has 1 dBi antenna gain. That may be, but it's not necessarily true. If that antenna gain is pointing up in the ceiling, if your peak is in that direction, it doesn't matter, right? So the patterns are critical as well. I guess you already know all this, right? How dBs work and logarithmic, and so a lot of zeros there. So I mentioned before already, the 655 has 3 radios. They're all 4x4 MIMO. The 2.4 and 5 gig radios are integrated into the SoC. They're part of the part that we buy from Qualcomm. The 6 gig radio is a separate dedicated radio that interfaces to that SoC using PCIe, so it has a digital interface, whereas the other radios communicate out of the SoC using an analog interface with the front end of the radios. You don't need to worry about any of this, but just highlighting the different parts that go into that. So the 6 gig radio is a little different, and we buy another part from Qualcomm called, it's their Pine chip that implements that. And again, all of them implement what's called front-end modules. Those front-end modules contain power amplifiers in transmit direction and LNAs, or low noise amplifiers, on the receive side to amplify the signals that are coming in. So that's basically the whole front end of the radio. Then we have BLE and Zigbee radio. As you know, they have multiple functions. They do beaconing, or they can serve as an IoT gateway. As a bonus, not many people know that, the BLE radio is also provides you a wireless console capability. Yeah, question?
I know it probably doesn't, but does the PCI interface affect the latency on the 6 gig radio in any way?
Does it interact? Does it?
The PCIe interface for the 6 gig radio, does it affect the latency of the radio in any way?
The link. Well, there's definitely.
Because the other two are integrated into the chip, whereas the other one you got to go through PCIe logic to get to.
No, it doesn't affect the performance. I mean, the PCIe interface is designed to do exactly that, to support an additional radio. And it's, when they built the Hawkeye chipset, they were building it for this specific use case, right? For a 6 gig high performance radio. There might be some digital interference, and that's why all the shielding is there. I mean, but other than that, there's no, the 6 gig radio, the 5 gig radio, from a high level view, perform very, very similarly. So there's really no difference. It's just the architecture of the part that we selected that works that way. It was originally, the Hawkeye chip was originally built for Wi-Fi 6. We use an earlier version of this in some of our Wi-Fi 6 products. We now took it and then we added a 6 gig radio to support Wi-Fi 6E as well. Yeah, so you can do, if you get an app and that you run on a tablet or a smartphone, you can actually access the console interface and interface with it that way instead of that RJ45 or custom console cable. So you have another option to get to that. And yeah, you can, if you want, add a second or maybe even a third in the future BLE radio using the USB port, but not a whole lot of people do that. Yeah, I just wanted to give a shout out to Farhan again. There's lots of very innovative and, again, some patented filtering technology that we implement on the APs. We do not take radio reference designs from some of our chipset vendors and just put them in a box. We design our radios pretty much ourselves, and we have lots of innovative solutions just to make sure that the radios are as effective and as efficient as possible. So lots of work and thought goes into that. So yeah, lots of parts involved in radio. So I'm not going to ask you, because you guys are not really responding to my queries, my questions very much. This is 2.4, this is 5, and this is 6. Am I right? Am I wrong? Okay, good. So the parts look a little different. This is the 6 gig radio because there's just a little bit more going on there. It's not just the RF and analog part. There's this digital interface and a lot of conversion happening in that part as well. But as you can see, 4x4 radios, they each have their separate section, shielded off from all the others just to minimize coupling and interference between them. A lot of stuff happening on the backside as well, but not a lot of components there. I'm going to skip over this. It's not interesting. Why, you think it's interesting? You want to go over it? No, I'm not going to do it. So on the power side, as you know, right, you can do PoE or you can do DC power on the 655 or most of our APs. If you come in with PoE, the voltage range is, what do I say there? I have that somewhere here. I thought, I don't. Well, doesn't really matter. The typical voltage from PoE comes down at 48 volts. DC voltage is 12. Since we support both voltages, the first thing we need to do on the PoE side is convert it down to 12 volt. And then from 12 volt onwards, we go to a dozen, 15, 20 different voltages and different sources to supply power to each and every single component on the board. And all of those conversions, they have some efficiency associated with them. They need filtering, they need enough power there, we need to make sure it's clean enough. There's lots of stuff that goes into that. When we have DC and PoE powers attached to the AP, we take the DC source as a priority, PoE is secondary. And if we have two PoE sources, typically we would have hitless fill over between the two, or in the case of the AP655, we can also combine the two into, to provide more power to the AP. You guys familiar with IPM? So we have a little circuit, or some circuits actually on the board that continuously measure the actual power consumption of the AP. So we have that information available. So that is to deal with the fact, what I mentioned before, the power consumption of an AP can vary widely. And in many cases, you will never hit that maximum power consumption of the AP that we put on our data sheet. So it's really not necessary to apply massive restrictions. If your PoE budget is limited, and you know that your worst case is 41 watts, you don't need, since you never get to the 41 watts, you don't need to apply all those restrictions. By measuring the actual power consumption of the AP, we can postpone any of those restrictions until we really need it. So that's really what IPM does. It helps us to more efficiently use the power from a limited PoE source. And then we have the capability to put the AP655 and most of our APs into a deep sleep mode. That is something that we're exploring as part of the Green AP initiative. It's a little frustrating. We've been talking about Green AP for years. This feature is supported on the AP, so an AP under software control can be put into deep sleep mode. And that opens up a lot of interesting use cases where in a larger system, if areas of your network are not used, those APs can be put into sleep mode. Then when people enter that area and traffic goes up, we bring them out, get them out of the sleep mode. That is the idea and the vision that we've been working on for a long time. We're finally getting to a point that it's being delivered. It's really the management side or the system, or let's say the central side of things, where this is where most of the complexity is. On the AP, we've been supporting deep sleep mode for quite some time. That's where my voltage range was. So PoE varies from 37 to 57, worst case, depending on what PoE source you use. And then, yeah, as I said, we require multiple supply voltages. And then we go down to 12 first. Typical efficiency, we think is about right, 75%. If you look at the overall, what goes in on the PoE side and what gets supplied to all the components, it's about 75%, but it typically goes through a lot of conversions. And this is a little bit, I thought, I'm a little bit of a numbers geek, so I like to do this. 41 watts goes into the AP. What comes out of the AP other than heat? There's a bit of RF energy, and even if you're maximum 18 dBm, you can do the math, that's 63 milliwatts. With 12 radio chains, that's just 757 milliwatts that we're transmitting out as RF energy. Not even 1 watt. And on an Ethernet, we may put another half a watt or so on the wire. All the other energy that we pump into that AP, all that 41 watts, is just heat. So in the end, all we do, we process data, we transfer data, everything else becomes heat. And actually, that RF energy, over time, turns into heat as well. Ultimately, everything becomes heat, right? It becomes thermal energy. Too geeky? No? I don't know. This is not the 655, but I was lazy, I guess. I took this from the 325 and I didn't convert it. But it just gives you an idea of all that conversion that happens. So from DC power, it's pretty straightforward. We have 12 volt, and then we go into multiple conversion stages. From Ethernet, we first go down to 12 volt, and then we do the same. But it just gives you an idea that there's a lot of circuitry involved in just massaging all those power supply voltages. And as you can see, they're everywhere. Crisscross over the board. I may have made a few mistakes there, but I think it's pretty accurate. Most of this is PoE, and then lots of these are adapters and converters and whatnot to get all the voltages. GPS. Oh yeah. This was how my slide looked yesterday when I hadn't finished it yet, and then I decided to finish it, and then I did this. This is typical Atmosphere presentation preparation. We do last-minute stuff. I was thinking about taking that slide out. I thought I might as well leave it in. We have a GNSS receiver, which covers GPS, GLONASS, BeiDou, Galileo, the different global positioning systems. We're operating on the L1 band only. I think we're adding L5 in a future product, but whatever it may be. The antennas that we use for GPS on this product are very similar in terms of characteristics and shape as the Wi-Fi antennas. I get questions sometimes, why don't you have an external GPS antenna, all that, but that's just the way we implemented it. The GPS receiver or the GNSS receiver in the AP is optimized and designed for stationary deployment. So it sits there and it takes advantage of the fact that the AP is not walking around. It's not a cell phone, right? You don't need to update your location all the time. And you have a very sensitive radio as well. So we have good hope that even though an AP is indoor, if it's close enough to the side of the building, you can often capture a GPS signal. Normally people say indoor GPS doesn't make sense, but you would be surprised how, and actually I'm gonna ask the guys who deployed the network here, which are mostly 635s and 655s, to see if any of these APs were actually able to capture GPS. Probably not, but some may that are closer to the edge of the building. And we use that for a lot of interesting use cases, but that's a whole different subject. Yeah, it is important. Just want to highlight that tied to the GPS capability, and some of you might go to a presentation about open locate, and we talk a lot about this. GPS helps us to create anchor APs, and then once we have those anchor APs that know their location, we can use a mechanism called find time measurement, which is part of the 802.11 standard, where we do time measurements between APs. We basically send packets back and forth, and we measure how long it takes, and based on that, we know how far we are from that other AP. If you do that with a couple of those anchor APs, you can trilaterate and you can determine the location of that other AP, and you can then propagate that. So over time, all the APs, ideally, would eventually know their location. That's the idea, and that's something that we're investing in quite a bit. GPS is just this little piece here, both sides of the board. So GPS is pretty simple, it's just one part, and an antenna, obviously. So yeah, I talk about hardware all the time. I do want to highlight that we spend a lot of time doing more than just hardware. Ultimately, the software, you could consider that the heart and soul of the product, right? The hardware is there, is optimized, is great, is efficient, is very high performant. But to make it all work, a lot goes into the software. Obviously, the primary task of the software is to be efficient and process all those packets back and forth between the two main interfaces, the wireless side and the Ethernet side. Okay, I'm getting close. I have one more slide. I said we have great customers. We also have great partners that build our products. We don't have our own factories. We rely on companies like Sercom, you may have heard. We have WNC, there's a bunch of them. And they work very closely with us. They're basically part of the team that Farhan is in as well. When we build these APs, we design them, we work together with them. We own the design. They do, frankly, a lot of the hard work, right? All the work. And they ultimately also build the APs. And I talked to them and they gave me a video. I just want to share that so you have an idea how, and it's called labor and delivery, right? How an AP ultimately gets built in a factory. I just think it's pretty impressive. I'm just going to run this in a couple minutes. So SMT means surface mounted technology. Those are all the little components that basically sit on the board and that get basically glued on it, and then they heat them up. And so they put a paste on the board. Those little components get stuck onto that paste, and then they get heated, and that becomes solder, and the components are soldered to the board. Maybe I'll just shut up and let you look at it. Yes, it's not fully automated. There's still people in the production line as well doing some manual work. But it's pretty amazing how much of that work is completely automated. This, by the way, it's already a little old. This is a 315 production line, if I'm not mistaken. Oh, by the way, they told me I can show it. It says Sercom confidential. I have permission to show it, but they didn't want me to give it out. They all this robotics, how things move around, that's really their bread and butter, and that's what they invest, that's their IP. Have you been to Sercom factory? No, okay. Yeah, automated. So it basically takes the board, put it in a dedicated test station. The key thing in a production line like that is to make sure that it is a constant flow, right? And some of the steps in production take 5 seconds, other steps may take 20 seconds. And when they take 20 seconds, they do it 4 times in parallel, just to make sure that everything flows at the same speed. Okay, assembly. I can do that. I actually did the reverse, disassembly. I'm very good at that. But there's really not that many people involved, and I don't know the capacity, but there's thousands of units coming out of this line every day if we run at full capacity. Even labeling, everything is completely automated. Am I the only one who thinks this is cool, or you? I'm just like, okay. So yeah, and then they put APs into dedicated test fixtures. Those are often, shielded Faraday cages, so they put the AP in there, they close the whole thing, run their test, and take them out again and move them to the next stage. All right. Too long? Ultimately, we'll end up with packing and inspection. And when we do a pilot production run for new products, they very closely monitor the failure rate in each step of the production. And if it's not 99% no failures, basically the pilot run is rejected and we got to start over. It's very, very critical that there is really no failures and no fallout in production, that we can push out those APs at a high rate. Of course, it's not a consumer product. It's not millions of units a year, but it's still pretty high. This is interesting, by the way. When we put the AP in the box, in the end, we actually weigh each of them individually. If one component is missing, could be just an antenna, that would result in a weight difference, and that triggers a failure. I was talking to a customer before. They said the 503HR bundle that we received, there was no power cord in the box. I said, then you probably took it out, because I'm sure they tested the weight and it should have been in there. But we're going to figure out what happened there, though. They can pretty accurately measure all this. So this is the last piece where they seal the boxes. Again, everything happens automatically. Just wanted to share that with you. I thought it was cool. That's all I have. If you have any questions, thank you.